So a couple of people had some questions about homework section 3.4, number 9, and that's exercise 28 on the list of exercises. And for this problem, it's a sort of a tricky application of Galileo's formula. The problem says that a man on the 10th floor sees a bucket pass his window and hit the ground 1 second later. Assuming the floors are 4.9 meters high, from what floor was the bucket dropped? And I realize that depending upon your problem, you might have different numbers rather than the 10th floor. But for this solution, you'll be able to follow this method for other floors. So to start, I'm going to draw a picture. Let's get a diagram of what's going on. So here's my building, and there are two variables that we're interested in. We're interested in a time variable and a height variable. And this problem gives us some information. So we don't know what height the bucket is dropped at. That's our unknown that we're solving for, and I'm going to call that h naught, the initial height of the bucket. And we're assuming that it's dropped from zero velocity at some initial height. But we do know the time at this time. So this is when we first drop the bucket. We're going to call that time 0. And then at the height where I'm at, which in this case is the 10th floor, I'll label this as 10 floor, because the 10th floor in this case isn't going to be at a height of 10. That's going to be at a height of 10 times 4.9 meters. And so for my 10th floor, that's going to be equal to 49 meters in height. And we don't know what time it passes my window relative to when the bucket was released, right? It was released sometime up here, and then it passes by my window. I'm going to call the time that it passes by my window t star. This is some unknown variable as well that we're trying to solve for. But we do know that it continues falling, and the bucket hits the ground. It's going to have a height of 0 down here when it hits the ground. And we know that the time that it hits the ground is going to be exactly 1 second after I see it. So that's going to be at time t star plus 1. Now there are other ways that you can set this problem up to solve it, but this is the way that I'm thinking about it. The bucket is released at time 0. I see it at some unknown time t star, and then 1 second later it hits the ground at t star plus 1. Whereas the heights, I start at height 0, I drop down, or I start at the height h0, sorry. This is my unknown starting height. It drops to where my location is, which is at 49 meters, and then it continues dropping until the height equals 0, which is when it hits the ground. And this information is enough, and our formula, to be able to figure out what our h0 is and our t star is. So what formula are we working from? Our generic form of our Galileo's formula is going to be h of t, the height of an object falling under gravity, is going to be equal to the initial height plus t times v naught minus 4.9, sorry, I'm doing this in my head, 4.9 t squared. And recall that h naught is our initial height, which is exactly the height that the bucket is dropped at, whereas v naught in this case is equal to 0. And it's equal to 0 because we aren't assuming that the bucket is dropped by being like thrown to the ground or being tossed up into the air. It's just going to be gently released, meaning that it's starting with an initial velocity of 0. So with our initial velocity of 0, we get that h of t is equal to h naught minus 4.9 t squared. Why is this helpful? Well, we have some information from our diagram here that we can fill in. So let's start with our first piece of information. What information do we know given from our viewpoint? From our viewpoint, we know what the height of the bucket is. The height of the bucket is going to be 49 meters in the air, and that's going to be equal to whatever our h naught is, we don't know, minus 4.9. Instead of putting t squared, I'm going to call it t star squared, because t star is the exact moment in time that I see the bucket. And I can solve for h naught here, and I see that that means that h naught is exactly equal to, adding this to this side, 49 plus 4.9 times t star squared. That's one equation. I'll put an arrow next to it because this is one of the equations. And this is the equation that comes from our 10th floor. What's our next equation? We can also use the ending point here as an equation. So going back and plugging into my Galileo's formula right here again, we know our height at the bottom. Our height at the bottom is 0, is equal to h naught minus 4.9. Instead of t squared, notice that the time in this case is t star plus 1 squared. So I'll put another arrow here because this is our other equation, and I'm going to solve for h naught. And when I solve for h naught, I see that I get h naught is equal to 4.9 times t star plus 1 squared. Why is this interesting? This is helpful because now I have two equations. I have this h naught equation and I have this h naught equation. And the only variables here I have are my h naught, the starting height that I don't know, and my t star. And I'm going to solve for my t star to be able to figure out the h naught. Let's write this on a separate sheet of paper. So writing what we have, we know that in this case, our h naught is exactly equal to 49 plus 4.9 times t star squared, and that's also exactly equal to 4.9 t star plus 1 squared. These are the two equations that we came up. We solved for h naught, and these are the two things that it's equal to, so they better be equal to each other. So now we've reduced one of our variables, and I'm going to solve for t star, which is relatively straightforward. Notice that I can divide everything by 4.9, so I'm going to divide both sides by 4.9 just to make it a little nicer. And we see that we get 10 plus t star squared is equal to t star plus 1 squared. I'm going to multiply this out, and I see that I get t star squared plus 2t plus 1. Recall, because this is squared, this is not equal to t star squared plus 1 squared. Those two things aren't equal to one another. We have to be wary of the middle terms and use distributive property, or you're probably going to use FOIL. But that's equal to 10 plus t star squared. I can cancel a t star squared from each side. I just subtract them. And I see that that means that 10 is equal to 2t plus 1. Whoops, this should have a star. Sorry, when I multiplied this out, I just dropped the star. But that's just a labeling convention. So that means that t star in this case is exactly equal to 10 minus 1, which is 9 divided by 2, which is 9 halves. Great. Let's go back to our picture and label what we found. I'll use purple to write this in. So we just found that we see the bucket, our t star value, our t star value is going to be equal to 9 halves, which is equal to 4.5. So that means our time down at the bottom was 1 second later, and our time down here is equal to, 4.5 plus 1, 0.5 plus 1, 4.5, which is equal to 5.5. And from this information, we can go back to one of our equations here to be able to solve for h naught. And I think that this equation is a little bit easier, so this is the equation that I'm going to use. We see that h naught is exactly equal to 4.9 times 5.5 squared. So let's write that work out on this sheet. We saw from our other formula that h naught was equal to 4.9 times t star plus 1 squared. And we found what t star was. This is 4.5. So t star plus 1 is 5.5. I get 4.9 times 5.5 squared. I'm going to plug this into my calculator because I don't have these numbers memorized in my head. 5.5 squared is 30.25. Well, this is times 4.9. So this gives me my answer in meters. So this is saying that 0.2 meters is about equal to. But we don't want to give our answer in meters. Instead of meters, we want it in floors. And so to convert back, we actually just divide by this 4.9. It's sort of a convenient number that our floor height is exactly the same as this coefficient. But we just solved that this is our height in meters. So in floors, I'm going to divide by 4.9. and then I'll get back to my 30.25. So this is the number of floors up, and notice that in the problem, in small print, it says that they want you to round up to the next greatest floor. So that means that it wants you to round up to the floor, rounding up, this is my floor function, to 31.